This whole section of this class is basically about how microbes and humans interact with each other. We're going to be talking about today just basic interactions between humans and microbes, and then we're going to be talking about the human immune system, which is a huge part of how humans and microbes interact, and then we're going to talk about how microbes cause disease. Okay? And then the entire fourth section, so exam number 4, is all about specific diseases. We talk about specific bacteria and viruses, the diseases that they cause, how they're transmitted, the symptoms that they cause, things like that. Okay, so hopefully we're getting into the stuff that most of you as potential healthcare providers find the most interesting. I think that most people find this part a little bit easier. Globally, if you're concerned about it or curious about this, most people find exam number 2, just like in my class, exam number 2 has historically been the hardest. I think that's mostly because it's focusing on very small things like DNA and proteins and stuff like that, and that's hard for a lot of people. But moving into the disease stuff and the immune system, I think a lot of nursing majors and things like that find that more interesting and therefore more easy to study. But that may not be the case for you, but that is the case for a lot of students. So yeah, today we are moving on to Chapter 11, Interactions Between Microbes and Humans. And do notice that there are only 4 chapters in this section. That is correct. There are only 4 chapters. There's only 4 McGraw-Hill Connect assignments. The human immune system chapter there's actually 2 of them, are pretty intense. So we only do 4 chapters because there's a lot of material to be covered. All right, so we are going to be talking about how, again, humans and microbes, particularly bacteria, viruses, and funguses, interact with humans. We've kind of been talking about recently how microbes interact with their environment, right? We talked about oxygen and temperature and all of those kinds of things, how they interact with agents that we use to kill them, right? Heat and things like that. Now we're going to talk about how they interact with our human bodies. And that is going to be both good and bad. We're going to talk about how humans and microbes interact in disease states, right? Like how they interact when a microbe is causing disease. But there are also a lot of good ways that microbes interact with humans. And we talked about this kind of a lot in the first chapter, but we're specifically focusing in this part on how they interact with our human bodies, not just our environments and photosynthesis and all that fun stuff, but how they interact with us as humans. And one of the most important and most beneficial ways that microbes interact with a human is through the human microbiome. So the human microbiome is the sum total, so all the, it is the sum total of all microbes living in and on an individual human. Okay. The human microbiome is hugely important to the health of its human host. For the most part, the human microbiome is a good thing. It provides us with a lot of different things that we're going to talk about as we go through this. But occasionally it can be bad. There are ways that your human microbiome can eventually cause disease. So it is possible for the microbiome to be bad, but for the most part, we're going to focus on it as a good thing. And these are just some facts. As always, I don't expect you to memorize numbers. It's just some facts to keep in mind. That up to 90% of all disease can be traced in some way back to the gut and the health of the microbiome. And there is more evidence of this the longer we research this. They're now tracing all kinds of things to the human microbiome, and the gut microbiome being out of balance can lead to a lot of different things. There are studies to suggest that the human microbiome, specifically the gut microbiome, is linked to autism and ADHD and Alzheimer's, on top of all the infectious diseases that we know about. Okay, so there's a lot of information here, and it does a lot of good things for us. There are 10 times as many outside organisms as there are human cells in the human body. So your human body is made up of more microbes than it is of human cells. Just to kind of put that in perspective. Okay. And another thing that's kind of interesting is that the percentage of individual humans are identical to one another in terms of the host genome. So our host genome, like if I was to compare my genome to any one of yours, our genomes are 99.9% the same. Doesn't matter our gender or our race or anything else, our human genomes are 99.9% the same because we are all humans. That 0.1% is what makes us individuals, but the rest of it is all the same. However, the percentage of individual humans are different from each other in terms of the microbiome. So each individual person's microbiome is hugely individual. Okay, if I compared my microbiome to any of yours, our microbiomes will be anywhere from 70 to 90% the same. Okay, so our genes makeup are very, very similar, but our microbiomes may not be that similar. And that can have a lot to do with how individual humans react to bad bacteria or good bacteria based on the bacteria that they have in their guts. Okay, so again, you don't have to memorize any of these numbers. It's just to kind of put it in perspective for you a little bit. So when we're talking about the human microbiome, there are two words that we kind of associate with these interactions. And one is colonized bacteria and one is transient bacteria. And these are two ways that bacteria or other microorganisms can interact with a human. A colonized bacteria are bacteria or microorganisms that live with their host for long periods of time. So when we use this term, we use that term to mean bacteria or other microorganisms that stick around and live in or on your human body for many, many months or years. Okay? Most of us in this room are going to be colonized in our gut with Escherichia coli. Okay? Almost all of us will have E. coli in our guts. We are colonized with it. It lives inside of our guts almost our entire lives. Okay, so that is a colonized organism, something that kind of becomes a part of our environment for a long period of time. The other term is exactly the opposite. Transient bacteria are those that interact for short periods of time. Now, it's important to remember that transient doesn't necessarily mean disease-causing. You come in contact with bacteria, right? Touching this desk, I am coming transiently in contact with millions of bacteria and viruses, right? But the vast majority of things that my body comes in contact with are either not going to harm me at all, or they are going to be good. Okay, so transient just means short term. Doesn't mean good or bad or anything else. It just means it's a short interaction. Okay? Colonized, again, it doesn't necessarily mean good or bad or anything else. It just means that this organism is sticking around for long periods of time. So occasionally, bacteria or organisms from either group, either the colonized bacteria or the transient bacteria, can invade host tissues and cause disease. Okay? And again, that organism, the infectious disease, can come from either of those groups. So a bacteria that has been a part of your normal gut flora for decades, can all of a sudden something can change and it can take over your body and cause disease. Okay, so just because a bacteria has been around for a long time doesn't mean that it won't cause problems. I know I've talked about this before, but again, the infection that I had in my leg, that happened because of bacteria that was already in my body. That didn't happen because of something that was from the outside. What happened was I ended up with a cut, right? I had a wound on the outside of my body. I also had a broken pelvis and couldn't move. And it's really gross to think about, but it's the truth, is that I couldn't get up to clean myself. Okay? I was being taken care of by other people. I couldn't get up for anything, so just let your brain go where that will go. Okay? I had to do everything laying in a bed, and somebody else had to take care of me. So E. coli, from likely my digestive tract, moved into the wound and caused infection. So bacteria that had been sticking around for a long time suddenly moved from one place to another and caused an issue. Okay, so that was a colonized bacteria that suddenly became infectious. Sometimes it's something that we came in contact with very quickly. So it can happen either way. And this chart here, again, is not to, you don't have to memorize any of this. The point of this chart is to show that the human microbiome is incredibly varied. Not just from person to person, meaning my microbiome is different than any of yours, but within a single person. So the microbes that you have on your face are going to be different than the microbes you have in your respiratory tract. And those will be different from the microbes that you have in your digestive tract, which will be different from the ones in your genital tract, right? Everything on your body has a different environment, right? Your skin is oily and dry for the most part. Sometimes it's sweaty, but for the most part, your skin is oily and dry. The inside of your digestive tract is incredibly acidic, it's dark, and it's usually pretty moist in there. Okay, so there's a completely different environments. Different bacteria are going to grow in different environments. Okay, and so this is just to show you that, you know, the different parts of your body will have different microbes growing on them. Because different microbes like different environments. That's all there is to that. Okay, so these are just some facts to remember just as we go through talking about diseases. The first one is that all healthy people harbor potentially dangerous pathogens in low numbers. Okay, so all of us in this room have potentially dangerous microbes growing on our skin. Most of you are probably colonized with Staphylococcus aureus. Staphylococcus aureus also causes incredibly dangerous skin infections, but most of you have it already on your skin. Okay, a significant number of you are probably infected with Neisseria meningitidis, which is a bacteria that causes brain infections. But most of you have it growing in your throat with no problems. Okay, so it's all about context, I guess, when it comes to a lot of these different organisms. A bacteria in one context is perfectly healthy and safe and normal. A bacteria in a different context will cause disease and harm, possibly death. Okay, so when you're looking at infectious disease, it's not just one factor that's going to lead to disease. There are all kinds of interactions and different contexts that will dictate whether an organism can actually cause disease or not. And that's what we're going to spend a lot of time talking about. But a big part of your human microbiome is that your non-pathogenic microbes in your microbiota keep the dangerous ones in check. So you have more healthy or good bacteria growing on your body than you do bad bacteria. And I mean, categorizing things as good and bad is a little derivative, but we will for this class, is that mostly your body is made up of good bacteria. And just like any other organism, microbes take up space, they consume nutrients. There's only room for so many of them. So if 99% of the space is taken up by good bacteria, the bad bacteria is not going to have a leg to stand on. They are not going to be able to take over and cause disease a lot of the time because that good bacteria is keeping them in check. This term is called microbial antagonism. Antagonism just means that they fight each other, basically. The microbes are competing with each other for space and nutrients. Something else to remember is that all incoming microbes are going to encounter the microbiome of their host as part of their path to causing infection. We're going to talk about how microbes overcome the microbiome and get past the microbiome as a way of causing disease. And the microbes learn how to do that as part of what they need to do to cause infection. And then each individual's microbiome is different. The microbiome of a person will be culmination of their genetics, their environment, their diet, their medical history, their age, sex, stress levels, and many, many other factors. Okay? People living in the same environment, so people in the same families, people who spend a lot of time living in the same house, eating the same food, being in the same environment, will have similar microbiomes. Like my microbiome is probably more similar to my husband's and child's than it is to any of yours, right? Because I spend time with them. We eat the same food. We live in the same environment. We breathe the same air most of the time. But you guys, we don't. We see each other for an hour, a couple times a week. We don't spend a significant amount of time together. Our microbiomes are going to be very different. However, an individual's microbiome is going to vary. People's microbiomes are never 100% identical. I hesitate to say never, but usually not. Even, comparing me and my husband have lived together for 15 years. Okay, our microbiomes are probably really similar. We eat the same food, we live in the same house, we sleep in the same bed and breathe on each other's faces all night, right? So our microbiomes are incredibly similar. However, I'm a female and he's a male. Okay, our stress levels are different. Our genetics are different. So there is always going to be a difference. Okay, each individual's microbiome is going to be different from everybody else's. And that is going to play a huge role in how we individually interact with microbes in our environment. Because we've all been, in a situation where almost everybody in your house has the flu, but you're the one person that didn't get it. Well, why were you the one person that didn't get it? Who knows? But your microbiome may have a bit to do with that. All right, so I just want to talk a little bit more about colonization. Now, remember again that colonization are bacteria or microorganisms that live on your body or in your body for long periods of time. And the colonization of your microbiome is a huge part of your protection against bad microorganisms. So when does that colonization happen? The colonization of a human, for a long time, this is actually kind of interesting. This was something I learned when I switched to this textbook last quarter. So I was always told that colonization began at birth. But there's actually recent studies to show that colonization might actually begin in utero. So that even before a baby is born, inside the uterus, it is being exposed to bacteria inside the uterus, small numbers of bacteria. So colonization of a baby's microbiome, so the bacteria that are going to be living in and on the baby, begin even before birth. But a huge part of that colonization is going to be birth. So vaginal births in particular, vaginal births, right? It's called that because the baby passes through the vaginal canal. Well, vaginal canals have tons of bacteria in them. And as a baby passes through a vaginal canal, the fluids and things like that from the vaginal tract get in the baby's eyes, nose, mouth, ears, on their skin, in their genitals. It gets everywhere. I don't know if you've ever seen a newborn baby, but they're very covered in things, okay? It gets everywhere, everywhere. And all of that bacteria is what starts the process of their development of a microbiome. And it's an incredibly important part of the development of a baby's immune system. And we have written here that vaginal and C-section births contribute differently to the initial microorganisms. So there have actually been studies that show that babies born via C-section are more at risk, that babies born via C-section are more at risk of getting sick of infectious diseases in their first 12 months of life. Because babies born via C-section are cut out of the uterus abdominally. Where do they not go? They don't go through the vagina. Okay, so they miss all of that bacteria that is in the vaginal tract as it is removed from the uterus. And so there have been a lot of studies that show that babies that are born via C-section, because they miss that initial colonization or inoculation, that their immune system is slower to develop. Not that this means that their immune system is never going to develop or their immune system is always going to be weaker or anything like that. It's just that that initial colonization is a little bit slower. And this has become such a thing. There's been a lot of studies on this and I know this sounds weird if you've never had a baby, but there are studies that show that collecting the mother's vaginal fluids right after birth and applying them to the baby, if it is born via C-section, can be really helpful in their immune system. But the baby's colonization will continue after that. Colonization happens through breast milk, and not just breast milk, but through breastfeeding. Breastfeeding is very close contact of a baby's mouth and nose to its mother's body, or the person's breastfeeding its body. Breast milk has a microbiome of its own, but breast milk is not sterile. Just like cow's milk or any other animal's milk, it does have bacteria in it. And then close contact with any of the people around it, the diet, eating food, anything else is going to colonize the baby with microorganisms. Okay, and then their environment, the baby can pick up microbes from anything they come in contact with. And that will continue throughout their entire lives. Your microbiome is ever changing. Your microbiome doesn't stop changing when you're born. Okay, your microbiome is going to change throughout your entire life. In fact, I don't know if any of you have, I think some of you probably have, moved to Louisiana from somewhere far away. I moved here from California, and when I first moved to Louisiana, the bacteria and the pathogens wreaked absolute havoc on my body. My allergies, I had never had allergies in my life until I moved here. Because I had grown up, I had spent 22 years in California, and all of a sudden I was in this completely new environment, exposed to all different kinds of bacteria, all different kinds of allergens, and my body wasn't used to it. But 10 years later, my body has now adapted. Okay, so your human immune system will change throughout your life. But that colonization, the initial inoculation, happens possibly even before birth, but most certainly at birth. So infectious disease, like we said before, occasionally when we come in contact with a microbe, either through colonization or transiently, so something that happens quickly, that microbe can get inside of the human tissues and cause a disease. It can cause an infection. And again, infection can happen either through transient microbes or just encountered through colonized microbes. Okay, we're going to talk about what that looks like. And if I haven't said it before, I think I have, but infectious disease is any disease An infectious disease is any disease or change in a human's health that occurs because of an infectious pathogen or a microbe. Okay, and I know I've said this one before, but just in case we don't remember, a pathogen is any microbe capable of causing disease. Like we talked about all the way back in chapter 1, the vast majority of microbes that we come in contact with every day are either not going to hurt us or they're going to be beneficial. More than the vast majority do not cause disease. They're what we call non-pathogenic. There is a very small percentage of microorganisms that exist or that we call pathogenic, meaning that they are capable of causing disease. All right, but we do have to talk about, I think we brought this up before, but we're going to talk about it again. The difference between what's called a true pathogen and an opportunistic pathogen. Now remember that pathogen just means capable of causing disease. That's not a qualifying statement, right? Something isn't a little bit of a pathogen. It either is one or it is not. It is a yes or no statement. Is an organism capable of it or is it not? Yes or no? Okay, but there is a little bit of gray area when talking about pathogens, and we use true and opportunistic as a way of kind of covering those gray areas. So a true pathogen is an organism that will cause disease in a healthy individual a high percentage of the time. Not all the time, but in most interactions of that microbe and a healthy human host, that microbe will cause infection. So an example of that is the influenza virus. Okay, it doesn't matter how healthy you are. Most of the time, if a human comes in contact with the influenza virus, they will get the flu. Okay. Streptococcus pyogenes causes strep throat. Okay, again, it doesn't matter how healthy you are. Most of the time, when you come in contact with Streptococcus pyogenes, you are going to get strep throat. Now, true pathogens, another way of kind of thinking about this is they are not, okay, these are not usually going to be colonizers for the most part, because these bacteria or microorganisms cause infection almost all of the time. So they are not going to be able to hang around in our bodies for long periods of time. Okay, so the true pathogens are most often, not always, but most often going to be the transients. Okay, these are going to be the ones that come in for a short period of time, cause us harm, and then our immune system kicks them out. Okay. People are not typically colonized with the influenza virus, typically. Okay. There's always going to be, one of my favorite things to say is that bacteria don't read textbooks, okay? Not everything is going to be something 100% of the time, right? But our other type of pathogen are what we call opportunistic pathogens. And these are organisms that are generally low virulence. We're going to talk more about that term in a minute, but meaning that they don't typically cause infection. They can hang around, they can be colonizers. They only cause infection when a person is immunocompromised, meaning that their immune system is down, or something has changed to the microbiome, or there has been some change in the environment or something else. They're usually only going to cause infection when they're given the opportunity. Okay, so that's why they're called opportunistic pathogens. Okay? And the way that I kind of like to think about this is to not talk about bacteria, but to talk about something else. So like one of the ways that I describe this is like, I'm an opportunistic vegetarian. So what that means is I don't really like eating meat. It's not my favorite. I don't really like it. I'm not going to really eat steak. It grosses me out, which is a hot topic, I know. But I don't particularly like eating meat. But I'm not so morally opposed to it that I won't. I like hamburgers sometimes, right? I eat it sometimes. I'm an opportunistic vegetarian, okay? That's how bacteria are. If the opportunity is right, if just the right conditions are right, I will eat chicken for dinner. But it's not my original choice. It's not my favorite thing. It's never going to be my first choice. And opportunistic pathogens are kind of a similar way. Most of the time, they're just hanging out. Okay, they're not going to cause disease. They're just going to live in their environment. They're going to chug along, no big deal. But if something changes, the environment is right, the person's immune system is compromised, something else has changed, they will cause disease if it's given the opportunity. Okay, true pathogens are the true meat eaters. They're the people who would choose steak over everything else. Okay. So true pathogens will cause disease almost all of the time, even in healthy individuals. Okay, so things like Candida albicans and Haemophilus influenza, I know you guys don't know what those are yet, but we're going to talk about them later more. Candida albicans is the most common cause of yeast infections in humans. It causes vaginal yeast infections, oral thrush, things like that. But almost all of you, if we cultured almost every single one of you in here, almost all of you would have Candida albicans as part of your normal flora somewhere, either in your respiratory tract or your genital tract. Okay, most of the time, we don't have yeast infections, right? Most of the time that Candida albicans hangs around, doesn't do anything bad, part of our normal flora, no big deal. But if you are on antibiotics, or if you have COVID, or if you're a baby who has no immune system, sometimes that Candida albicans will take over and cause infections. Okay? So that's the difference between a true pathogen and an opportunistic pathogen. Now, another thing to look at is the definition of pathogenicity and virulence. So again, pathogenicity is the ability of a microorganism to cause disease. This is that's my coloring book if you guys are interested. Sorry. Whether a pathogen is capable of causing disease or not. Okay, so this is a yes or no question. An organism is either a pathogen or not. You cannot be a little bit of a pathogen or a lot of a pathogen. It's yes or no. Is an organism a pathogen? Yes or no. However, in order to qualify how easily an organism can cause disease, we use a couple of different terms. The first one is infectivity. So infectivity is how easily an organism can cause disease. Okay. If something is very virulent or has high virulence, that means that it causes disease a lot of the time. Okay. Or if it's highly infective, I got my words mixed up. If it's highly infective, right, it's highly infectious, that means that it's going to cause disease a high percentage of the time. Virulence is how serious the disease an organism causes. Okay, so for example, we have 3 diseases here. Chicken pox, I know most of you have not had chicken pox because most of you have been vaccinated against chicken pox. But before vaccines for chicken pox existed, chicken pox is highly infective. If you are within breathing distance of somebody who has chicken pox, you are almost certainly also going to get chicken pox. Chicken pox tears through families, schools, anywhere where kids are near each other. It's highly infective. Another word that we use for infective, kind of colloquially, is contagious. It's highly contagious. That chicken pox is going to spread from person to person incredibly easily. Chicken pox is great at causing disease. It is highly infective. However, chicken pox is low virulence because the vast majority of people who get chicken pox are itchy for 2 days and then they're fine. Okay, the disease that they cause is not typically very serious. Okay, so they're highly infective, but they have a low virulence. Tuberculosis, on the other hand, is exactly the opposite. Tuberculosis has actually a pretty low infectivity, especially in today's world. The chances of you becoming sick with tuberculosis, even if a person you are sharing a bed with on a regular basis has tuberculosis, is actually very low. So being around somebody with active tuberculosis does not mean that you're going to get it. So tuberculosis is actually not very contagious or infective. Those words are kind of interchangeable. It has low infectivity. However, tuberculosis has very high virulence. If you do happen to get tuberculosis, it is incredibly dangerous, and it will cause death in almost all the people who are not treated for it. Even people who are treated suffer permanent lung damage and other things like that. It is a very serious and deadly illness, so it is highly virulent. Okay, and then the last one is something like smallpox. Smallpox, which has been eradicated, so nobody knows anything about this, but the reason that smallpox was so dangerous when it did exist was because it was highly infective and highly virulent. It spread like wildfire through communities, and it killed almost everybody it infected. So it's highly infective or contagious and highly virulent. Okay, so that is something that you'll have to think about as we kind of go through all of these different infections and we talk about how these bacteria and viruses and things like that interact with human bodies. We're going to talk about their infectivity and their virulence. Okay. Because again, all of this is a balance, right? Like we've said before, we are never going to be able to get rid of all the bacteria or all the viruses. It's not going to happen. It's completely unrealistic. And even if we did do that, our environment would cease to exist and our entire world would collapse. So it's not going to happen. It's a balance between how much do we protect ourselves from specific organisms based on how likely they are to make us sick, and if they do make us sick, how serious is that illness? Okay, there's a reason that if you think about like comparing the common cold and the flu, those two things, the flu and common colds actually probably have pretty similar infectivity. Okay, influenza and like rhinovirus, which causes the common cold, are similarly infective. They are just as contagious as each other. However, influenza is much more likely to cause death and long-term issues than the common cold, which is why we have treatments and vaccines for influenza. But if you get a cold, they just tell you to go home, right? Drink some fluids. There's no treatments for the common cold. There's no vaccine for the common cold because it's not very serious. It's much less virulent. Okay, so now we're going to talk about specifically how bacteria cause disease. So pathogenesis, remember pathogen is a bacteria capable of causing a disease. Pathogenesis, genesis is the creation or beginning, right? Genesis means the creation of something, that suffix genesis. Patho means disease. So this is how bacteria cause disease, how they go through the process of causing disease, what steps they take, and all that fun stuff. So we're going to talk about, there are 5 stages of pathogenesis. We're going to talk about all 5 in detail, but this is the 5 laid out. Most of this is pretty intuitive. Again, the first step is finding a host. The second one is attaching to it. The third one is getting into the host. The fourth one is causing damage. And the fifth one is leaving. Okay, so it's pretty intuitive and self-explanatory, but we are going to talk about each one individually. Okay, so step 1 of bacterial pathogenesis, all of these steps have to do with bacterial pathogenesis. Step 1 is exposure. So the first thing that a microbe has to do, and we're going to kind of look at this from the perspective of the microbe, right? What the microbe is trying to do and the goal of the microbe, not the goal of the human, right? The goal of the human is to not get sick. We don't want to get sick. But we kind of want to look at this from the perspective of the microbe. The microbe is attempting, and its goal is to make us sick. It wants to, or not even to make us sick, it wants our nutrients. That's how it survives. It doesn't care about making us sick, it just wants our nutrients. Okay? So step 1 is going to be exposure. So in order to cause disease, this microbe must first gain entry into a host. And there are two ways that this can happen. It can happen exogenously or endogenously. Now, remember those prefixes. We've talked about those prefixes a lot. What does this exo prefix mean? It means outside or from the outside. And then endo is just the opposite. It means from the inside. So a bacteria can gain entry into the human either from the outside, meaning that it came from the environment, or it can gain entry from inside. Okay, so a bacteria that is living inside your human gut and not causing any problems can all of a sudden gain entry into your bloodstream. Okay, so that's endogenously. Exogenously would be like somebody sneezes on you with the flu and the flu virus gets up your nose. Okay, that's endogenously. It's coming from the outside. Oh, God, I got it backwards. Sorry, it's hot up here. Exogenously is like the outside. So this would be like the flu, okay? Like when somebody sneezes on you with the flu. I'm sorry, I keep mixing up my words today. Somebody sneezes on you with the flu, that virus is coming from the outside. That is exogenously. Exogenously. Outside. Exo, outside. Endogenously would be like a bacteria coming from the inside. So a bacteria inside your GI tract invading the bloodstream. Okay. So a bacteria or a virus that was already inside your body, part of your normal microbiome, colonized within you somewhere, has now infected you, gain access from somewhere. Okay, and a portal of entry is an anatomical site through which pathogens gain access to the human body. Okay. And portals of entry are, for the most part, going to be, and this is a kind of weird way of thinking about it, but it's true. So it's either going to be a natural or an unnatural hole in your body. Okay, so most of your body is covered with skin. And your skin is a very tough outer layer. We'll talk more about this when we get to the immune system. But your skin is going to block just about everything. There are incredibly few microbes. I can think of one that are capable of crawling through your skin to make you sick. Okay? Most viruses, bacteria, things like that are not going to be able to do that. So where they actually get through to make you sick are the unnatural holes or the natural holes. So your natural holes would be like your nose or your mouth or your ears or the pores in your skin, right? Your sweat glands, even really, really tiny holes. The urethra, the vaginal tract, the anal opening, right? Those are all holes in your body. There are areas of your body that you don't have skin. And if you think about it, think about all the infections that you have had in your entire life. Most of them probably happened because of something getting into one of those holes, right? You get the flu or the cold or a cold or something like that through your nasal passages. Strep throat you get through your mouth. If you've ever had pink eye, that's something getting into your eye. Ear infections or things getting into your ears. Urinary tract infections or something getting into the urethra, right? That is something getting into a natural opening in your body. Unnatural openings are things like cuts or wounds or needle punctures or surgeries or anything like that where there is an unnatural break in the skin. A mosquito bite, something puncturing the skin. Okay, so portals of entry for the most part are either natural or unnatural breaks in the skin. Okay? That is how most organisms are going to find their way inside of our human body. One that could be not really considered a break in the skin, though it kind of is, I don't know how you want to think about it, is the placenta. The placenta is an organ that exists inside of a uterus. It's what it feeds a baby while a baby is in there. And there are certain bacteria and things like that that can actually cross the placenta and then get into the fetus. So that's not really a break in the skin, that's kind of an exception. But everything else, right, the eyes, the nose, broken skin, the urethra, anus, a needle puncture, insect bite, right, those are all either natural or unnatural breaks in the skin where we don't have skin. And it's important to remember, we're going to talk about this later more, that there are some organisms that have very, very specific portals of entry and some that don't. For example, influenza is very specific. Influenza is only going to infect the nasal opening. If influenza comes in contact with your body anywhere but your nasal opening, it is not going to cause disease, right? You can't have gastrointestinal influenza or genital influenza. That's not a thing that exists, okay? So influenza is a very, very specific, or has a very specific portal of entry. Some organisms, like E. coli, is more diverse. If you ever work in a hospital, you're going to realize that people can have E. coli infections basically anywhere. You can get E. coli in your eyes, your nose, your mouth, your ears, any kind of wound. You can get it in your lungs, you can get it in your GI tract, you can get it in your genital tracts, you can get it anywhere. Inside your spinal column, inside your organs. E. coli doesn't care where it goes, okay? So its portals of entry are very diverse. E. coli can enter pretty much anywhere and cause infection. Influenza, more specific. And a lot of organisms are going to fall somewhere on that spectrum. Sometimes they have one portal of entry that they can use. Sometimes it's a couple. Sometimes it's many. But each organism will have a specific thing that they must follow, I guess is the way to think about it. Okay, and the last thing we want to talk about here is infectious dose. So the infectious dose of an infection agent is the number of particles that must gain entry before they can cause disease. Okay? So some organisms have very, very low infectious doses, okay? Which means that something like norovirus, I think norovirus, I don't know the exact number, but norovirus it's like less than 10 particles. Okay, it has an incredibly, incredibly low infectious dose, which means that less than 10 particles need to enter a portal of entry in your body in order to cause disease inside that human. A very, very low infectious dose. Sometimes some organisms will have a very, very high infectious dose. So cholera is a bacteria that causes a gastrointestinal illness, but cholera's infectious dose is approximately 1 billion particles. Okay, so that's a big difference. In order to get the disease cholera, you must get over 1 billion individual bacterial cells inside your body. Okay, so I want you to think about it for a second. Don't say it out loud quite yet. I want you to think about it for a second. Of those two, norovirus, which has an incredibly low infectious dose, and cholera, which has an incredibly high infective dose, which one is more infective? Or which one is more contagious? Think about it for a sec. You guys can talk to each other, see if you can figure it out. So of those two, norovirus or cholera, which one is more infective or contagious? So think about it. I'll give you like 30 seconds. I want you to try and puzzle it out if you can. All right, everybody got your answers? Which of you thinks that norovirus is more infective? Okay, which ones of you think cholera is more infective? Okay, most of you got it right. It's norovirus. Because if it requires less bacteria or virus to make you sick, it is better at being a pathogen. Okay, so think about it if we were talking about who was had a better basketball shot. Okay, and we were testing this by saying who can make 10 baskets. We're shooting basketballs. If it takes me 1,000 shots to make 10, and it takes you 12 shots to make 10, who's the better basketball player? The other person, the person who took 12 shots to make 10, right? Because it took them less shots to do the same thing. It's kind of the same thing with norovirus and cholera. Norovirus requires much less virus to cause disease. Cholera requires much, much more. So those two things, infective dose and infectivity, which I know sound very similar, have an opposite relationship. The lower the infective dose, the higher the infectivity. So let me see if I can. Okay, so the lower the infective dose, the higher the infectivity. Okay. If something requires less amount to get in, if they only require 12 shots to make 10 baskets, they are a better basketball player. The lower the infective dose, the higher the infectivity, and the opposite is true. A higher infective dose means it has lower infectivity. Okay, so that is the first step of an organism, specifically a bacteria, causing disease. The first step is that it has to come in contact with the organism that it wants to make sick. That first step is called exposure. That microbe must gain entry into the host, must come in contact with a portal of entry. Yeah. Did I do it backwards? Low infective dose, no. I don't think so. So like in this case, norovirus has a very low infective dose. It only requires 10 particles to make somebody sick. So it is more infective. It's more contagious. It is able to make somebody sicker faster and better. High infective dose. Yeah. If something requires 1,000 shots to make 10 baskets, right? They require 1 billion particles to make somebody sick. They are less good at making somebody sick. So they're less infective. All right. So step 2 is after you come in contact with the host, step 2 is sticking to it. Okay, so step 2 is called adhesion, which means the process by which microbes become established in the host. Basically means that they grab on and don't get kicked out by the immune system. Okay. So step 2 is adhesion. It's the capability of pathogenic microbes to adhere to their portal of entry. And this is where the bacteria or pathogen in question, the one that's trying to infect, is going to come in contact with this host's microbiota and their immune system. So I guess we talk more about the immune system in a second. Okay, so for example, the influenza virus that is coming in contact with your nasal mucosa is also going to come in contact with the billions of bacteria that live in your nose. And the pathogen that is trying to cause disease has to have a way of dealing with those different problems. It has to have a way of getting past the microbiota. It has to have a way to physically grab on to the tissue that it wants to infect. Okay. And there's lots of different ways that bacteria can do this. We're not going to talk about anything in specific, but there are a lot of different things called adhesion factors. And adhesion factors can be spike proteins and adhesion molecules and cilia and hooks and spikes and biofilms. There's all kinds of different stuff. We're not going to talk about them individually. But each pathogen has some factor that makes it able to adhere to that portal of entry. So something that it uses to grab on and stick to whatever that portal of entry is. And level of infectivity and virulence depends on this adhesion factor. Okay? Because if an organism has a really, really, really good adhesion factor, if it's really, really good at grabbing on and sticking, then it is going to be better at causing disease. Okay, some organisms have less effective adhesion factors, and so they're not as good at causing disease. So the adhesion factors, we're just going to talk about them kind of in general, have an impact on an organism's infectivity and virulence. And again, some pathogens have very, very specific adhesion factors and will only be able to interact with a specific environment. Again, like the flu virus. The flu virus is only going to be able to stick and infect the nasal mucosa. Anywhere else, it is not an effective pathogen. Something like Helicobacter pylori, and again, you don't have to write that down, I'm not writing it down, is an organism that causes stomach ulcers. It is only really infective inside of the stomach lining of humans. Anywhere else, it's not going to do anything. So some organisms have very specific adhesion factors. Some organisms have more diverse adhesion factors. Just depends on the organism. Okay. And again, we're not going to talk too much about this in specific, but the bacteria will have to interact with the host's microbiota. If a host has a really strong microbiota, an organism might have a harder time adhering because that microbiota is going to kick them out. So this is kind of where the microbiota comes into play. A weaker microbiota makes it easier for things to infect. And the things that are infecting have to have a way to get past that microbiota. Some of them are better at it than others. It's just going to depend on the organism. But the important thing to remember there is that step 2 is adhesion, and it's basically sticking the pathogen to whatever it is it's trying to infect. Okay. So the third step is surviving the host defenses. So human hosts in particular, we have immune systems. And we are going to talk a lot about the immune system in the next 2 chapters. We're going to get into the specific parts of the human immune system in great detail over the next week or so. But it's something to think about is that bacteria have to be able to survive the human immune system if they want to cause disease. And any organism that does cause disease inside of a human, every time you've gotten sick, it's because a pathogen has successfully evaded your immune system. And they were able to get past all of your defenses and make you sick. But specifically here, we're going to talk about the details of the immune system later. But in specific, I want to talk about something called phagocytosis. So phagocytosis, this prefix phage, P-H-A-G-E, phage, where we say it phagocytosis in this word, means eating. So that prefix just means eating. Like dysphagia in humans means you have trouble with eating or swallowing. But phagia, phagocytosis, means eating. Cytosis just means cell. So phagocytosis as a word means cell eating. And phagocytosis is something that special white blood cells within your human immune system do. Okay, so There are white blood cells within the human immune system where their only job is to perform phagocytosis, which basically means they're called phagocytes, which basically means that they consume foreign particles, particularly bacteria or viruses, and digest them. They swallow them and chew them up and get rid of them. Okay, and you have these white blood cells, I think of them like patrolmen. They patrol your entire body at all times looking for things that do not belong. And if they come in contact with something that doesn't belong, that white blood cell will swallow it and kill it. Okay, so bacteria or viruses or any other microorganisms that want to invade your body have to have a way of getting past your phagocytes or evading phagocytosis. And this, like I said, this is a very effective mechanism. Your white blood cells are really, really good at doing this. So for an organism to be able to cause disease, they have to have figured out a way around this. And there are many organisms that do that. They have adapted ways to evade phagocytosis by a lot of different mechanisms. Some bacteria are capable of killing the white blood cells. So the pathogen itself, the bacteria or the virus, kills the white blood cell before the white blood cell can kill it, basically. Sometimes they form something called a capsule, which we talked about, I think, back in chapter 1. But the capsule basically works as like a disguise. It hides the bacteria from that white blood cell, makes it so it like covers itself in an invisibility cloak, right? It's like a little capsule so that the white blood cell can't see it. Okay? Or the kind of idea, I call it like the Trojan horse. The Trojan horse move. Sometimes bacteria or viruses have learned to live inside the white blood cells. So they wait to be swallowed up by the white blood cells and then they live inside there. Some of the most dangerous infections are capable of doing that, specifically the Black Plague. That's why the Black Plague is so dangerous, is because the bacteria that causes the Black Plague lives inside your white blood cells. And then your white blood cells carry it back to the center of your immune system, like your bone marrow. And then that bacteria is able to live inside your bone marrow and causes havoc. That's why it's so deadly. But there's lots of different ways that bacteria have figured out how to get past these white blood cell patrollers that are going to kill them. They either kill them first, they hide from it, or they figure out a way to live inside them. There are lots of different mechanisms. But any organism that is trying to infect your body has to have a way of getting past your immune system. Like I said, we're going to talk a lot more about the immune system later. But phagocytosis is one of the first steps of the immune system, and it's a big part of it, so that's why we discussed it here too. Okay. The fourth step is causing disease. Okay, so it's the process by which the microbe invades its host tissue and causes harm. And that's what the disease is. It's harm or change caused by an outside force. Okay? And there's a couple of different ways that microbes, bacteria, viruses are capable of causing harm. And we're going to talk more about signs and symptoms in a little while. We might get to those today. But there's a couple of different ways that organisms can cause harm or damage to its host. And those kind of fall into two major categories. The first one is that bacteria or virus is able to produce basically poisons, I guess is the best way of putting it. They're able to produce substances that cause direct harm. So they're enzymes or toxins that cause direct harm to human tissue. For example, Streptococcus pyogenes, the organism that causes strep throat, produces a toxin that dissolves your tissue. It dissolves human cells. That is why strep throat hurts so bad, because the bacteria is literally dissolving and killing and chewing through the tissue in your throat. It hurts. Streptococcus pyogenes is also capable of doing something called necrotizing fasciitis, which means that it chews through all of the skin on the outside of your body. Okay? It's producing a toxin. It's basically a poison. Or it can produce enzymes that chew through all different kinds of stuff. But these enzymes or toxins are substances that directly harm the human host. Okay? Now, the other way that they can cause harm is actually indirectly through our own human immune system. So when organisms invade our human body, our immune system is trained to respond. And sometimes that response can work against us. So the damaging host response is indirect damage through the immune system. Okay, so a kind of mild example of this is a fever, right? A fever is a symptom or a sign that's typically associated with a lot of different infections. Bacterial infections like strep, the flu, all kinds of things cause you to have a fever. Now, a fever is not something that the bacteria is causing directly. That bacteria or virus isn't doing anything to make your body heat up. The fever is caused because your body is trying to heat up to get rid of whatever's infecting you. Okay? So that sign, that symptom that you're having, the thing that makes you feel like garbage, is actually your own immune system. Another one, like the flu, or I guess this is a better example. When you have the flu or any kind of GI anything, when you have a GI bug, you have a stomach bug, what do? You throw up, or you have diarrhea, right? That's your body's attempt. That is something that is causing damage to you. It's uncomfortable. It doesn't feel good, but your body's doing that to try to get rid of everything that's in your stomach. It's trying to protect you. So there's this damage, indirect damage that can be caused from your own human responses. An extreme example of that is something called sepsis. And we'll talk more about sepsis later, but sepsis is something that happens when you have a bloodstream infection. And in an attempt to kill and get rid of the bacteria in your blood, your body will actually cause the blood pressure in your body to drop, which can cause you to faint. It can cause all different kinds of symptoms. It can actually also cause permanent organ damage. But your body is doing that to try to protect you from the bacteria in your blood. So indirect damage like sepsis, fevers, vomiting, a lot of like aches and pains that you have, body aches that you get when you're sick, when you have the flu. Like a lot of times you'll get sick like in your armpits and your groin, all your joints. That's your immune system working overtime to try to get rid of the infection. So damage goes in two parts: direct damage caused by the organism itself, and then the indirect damage from your body trying to get rid of it. Okay, so there's two different categories. All right, and we will talk about signs and symptoms next time.